Okay. From current slide. Okay. It'll come up one of these days. Now, as soon as it comes up. Now, I don't remember if it did this Monday or not, and this is going to be kind of strange. At some point one day, the projector sort of started strobing a little bit, and I didn't know why. Not seriously, but just enough to almost give you a headache. But yesterday, my computer started blinking in and off with a bad connection in the plug-in here. In fact, last evening's class, it took me half an hour to get it to even connect. I was pushing, pulling, twisting, doing all sorts of things, trying different plugs, variety of things, and then finally got it to work and taught my class, but we lost a half hour. And then this morning, it took a little bit of effort, but then I got it to work, and it's worked ever since. So what I'm saying is, when it blinks because of electrical, this will go dimmer. Now, it'll look a lot like the strobing from before, but it will be slower and not as weird. So if you see that happening, tell me so I'll come and look, because my battery will run down really quickly because the battery is sort of not in the greatest shape. Okay. So, just to let you know, whoops, that. Let me get my pen set up. There it is. Okay. Now, any questions on anything we've done so far? All right. My memory or mark here is that we're on page 476. If you got a text, I don't know if you do or not. Example 3, which is finding an arc length. Does that sound about right? Okay, that's what my memory was too. Okay. This one's not on the slide set, so let's work it out. Find the arc length of the graph of y minus 1 cubed is equal to x squared on the interval 0 to 8 shown in the figure. Now, I don't want to draw the figure for you, so I'd rather show you the figure. For people at home, they don't get to see it, but they should be. No, oh, I did say that. Okay. Here is the graph. Y minus 1 cubed is equal to x squared. Kind of looks a little bit like an x squared function, but that would be a little bit more curvature here. But you sort of get the general idea. Of course, x is 0 and y is 1, so that makes sense. And then it goes here. There aren't any negative values for let's see. Seems like there could be negative values for x. Well, I don't have to show any. But it's only doing from 0 to 8, so that's all they show. Okay. There would be things over here too, but they're not going to show those. Okay. So 0 to 8 is just what they're showing there. It kind of looks like a square root function, but not quite. Okay. Maybe no reason it should, but it kind of looks that way. Now, we want the arc length of that thing. What's the steps to go through to get the arc length? What's one of the first things we do? Take a derivative. Sounds like, ooh. How do you take the derivative of that? Say again? Oh, he wanted to do that, huh? Okay. Okay. That is doable. You could take the cube root of both sides. That would be y minus 1 is equal to x to the 2/3 power. And then add 1 to both sides and try to go like that. And that is perfectly good. Anyone think of another way? And we can do it that way, and it'll work quite nicely. Anyone think of another way we might do it? Does the word implicit come from? Probably not. Okay. Okay. Implicit differentiation. You take the derivative of this side, with respect to x and the derivative of that side with respect to x, and go forth. Which way you want to do? Infinite way or implicit way? Either way will work. You want to see them both? Okay, I was afraid of that. Okay, yeah, that will be fine. So let's do implicit first. Derivative of the left. What would be your first statement? 3 times y minus 1 squared. But then you got a chain rule thing to do here, because you're doing with respect to x, so then it will be followed by a y prime, right? Because you're taking the derivative of what's on the inside with respect to x, okay? So that's followed by a y prime equal to what? This is the easy part. 2x. Derivative with respect to x of x squared is 2x. You don't need an x prime there because you're taking with respect to x, and dx is 1. So that's okay. That's your dy dx here. Okay? The disadvantage of this is you still got to do it Anthony's way, okay? Because you still need to solve for this. And what your y was here, as we said before, is you did follow it, didn't you? That y minus 1 cubed is equal to y minus 1 is equal to x to the 2/3 power, right? That's taking a cube root of both sides and then adding 1. Okay. So what this would give you is y prime is equal to 2x over, and then you divide by this thing, over 3 times, and what your y is x to the 2/3 plus 1 squared. Okay. Now that's pretty messy. Okay. So I think actually Anthony's way is much better. There are some problems you're not going to be able to solve that explicitly for y, and then you do need to do implicit differentiation. This case is not one of those. So let's not do it, because we're going to need this later, and that's going to get really messy if we try to fiddle around with that. So let's go back to Anthony's way, okay? But I did want to at least remind you of what implicit differentiation was. Whoa! That wasn't the one I wanted. This is what I wanted to erase. I'll write that back. Okay? I'll straighten that up too. Okay. That was y minus 1 cubed is equal to that. And since I erased everything else, erase that leading coefficient there. And first step is to rewrite this as y is equal to x to the 2/3 power plus 1. That's far easier. Now do a y prime. And what's that? Two-thirds x to the what? Not quite. Negative 1/3. Subtract 1 from 2/3 and you get negative 1/3. Okay? Now, that's your derivative. Okay? Wonderful looking derivative, isn't it? Did I write the problem right? Yeah, okay. I was just trying to find in the book. Yeah, so that's right. A little bit louder. What's that?
Never mind, I was thinking about anti-derivative.
Okay. Now, I don't know if this is what you were thinking, but if you were, it's a good thought. This is not defined with this n. Okay? Because this x is in the denominator because of the minus sign there. So the derivative is not defined on the closed interval. It is on the open interval, or at least open on this end, but it's not on the closed interval. But that's not an issue. This is defined there, okay? The derivative is not defined on this end. So that may be something that will raise its ugly head later, but right now it's going to be all right, I think, I hope, okay? Now, oh, but that is a problem, though. Yeah, because what we were going to do, when we actually do the integration, that would wind up being a problem that we would have real difficulties with, okay? And so it is more serious than I thought. Because dy dx is undefined when x is equals 0, the arc length formula with respect to x cannot be used. Okay, I didn't know it was that bad, but it can. Okay? And solving for x in terms of y then, so we don't do it either way, but what we do is, let me go on and erase this because I don't have much boardroom. Okay? We're not doing it Anthony's way or the highway. What we're going to do is solve this for x and then change our formula around. Okay? Now, one reason we could do it, if you look at this again, this is a one-to-one function, right? It not only passes the vertical line test, making it a function, it also passes the horizontal line test, making it one-to-one, so it does have an inverse function. And I just lost what my first class is, but I've got another piece of paper in there. Second place. Okay. So we can do it for x. In other words, we're really going to shift it around. Same arc length, we're just going to reverse our axes, so to speak, without reversing the axes. So what we'll do then is solve this for x. And what would that be? X is equal to y minus 1 to the 3/2 power. Now what we're going to do is dx dy, okay, which is something we're not used to doing, but it'll still work okay. What would that be? I want to say x prime, but I'm afraid you might not, so I'm going to write it out. dx dy is equal to 3/2 y minus 1 to the 1/2 power. Okay? Now, you don't need a dy in it because you take it with respect to y. Everything is hunky-dory right now. Don't have any negative exponents, don't have anything in the denominator, so you don't have to worry about y equal 1. That's no sweat for that to be 1 because it's not in the denominator. So we're in okay shape then. Okay? That's going to change our formula slightly, so we'll have to remember that. But another thing we need to do is change our limits, because these were x limits, right? So we're going to have to figure out what the y limits are, but maybe not yet. We'll put that off till tomorrow, because tomorrow's another day, okay? So in fact, let's go back to Anthony's way and write that down again. Y is equal to, what was that again? X to the 2/3 plus 1, right? We'll use that to get our y values. When x equals 0, y is equal to, this is x's. When x equals 0, y is equal to 1. When x equals 8, anybody? 5. Excellent. So these will be the limits on y. Now we could have done that, or we could have looked at our handy dandy graph here and seen that's going from 1 to 5. 1, 0 to 8, 5. So we didn't have to do that, but I thought it would be fun to do it that way. I wanted to use Anthony's formula somewhere, okay, so why not? Okay. Now, where do we go from there? We got dx, dy. What else do we do? Square it. Okay, so when we square dx, dy, what does that become? Not that bad. Help me, somebody. 9/4 y minus 1. Oh, that's nice, isn't it? Okay. And then what do we do with that? And let me expand that just a little bit. Make it 9/4 y minus 9/4. There's a reason why I did that. Anyone guess what it is now? You got to add 1 to it. So why don't we add 1 to that rather than something in parentheses? Add 1 to this and 1 to that. And what does that give us? 9/4 y plus minus 9/4 plus 4/4 is minus 5/4. Boy, that 5 is showing up again, isn't it? Get out of there. Okay. All right. Now, what do we do with that then? All right. Your arc length S is, we're going to take a square root of it, and that's going to be our integral. So it's going from, and these are in terms of y, so we're going to have dy's out here now, okay? And we're going to integrate, so let's just do the integral from, this time, 1 to 5. That's why we needed the limits in y, okay? We needed to do that at some point, okay? And this will be the square root of 9/4 y minus 5/4 dy. Now, can anyone think of anything you can do to that to make it maybe a little less ugly or more palatable or something? Any ideas? One thing is denominator of 4, square root, pull out a 1/2 here, right? That would make it look nicer anyway. It might not be any easier to do, but it sure will look a lot better. So I'm going to come up here and do that. S is equal to 1/2 the integral from 1 to 5 of the square root of 9y minus 5 dy. And in general, I don't like to do square roots anyway. So let's write that as 1/2 integral from 1 to 5. Write that in not radical notation, but exponential. 9y minus 5 to the 1/2 power dy. I like that a lot better. Are y'all in agreement? Okay. Now, there's a couple ways you can go here. If it's all right, I'm going to erase some of this so I'll have more room to keep writing. Is that all right to do that? Okay, I think you got it all. Okay. What would be your preferred track to take to try to solve that? Okay. Looks like one of the players is getting a little tired, making the coach should. Substitute. Okay, why don't we do a substitution here? All right. Okay. What might we choose to substitute? Oh, yeah, let's do that. Let. Now, you don't have to do this. You can do it straightforward, but I thought maybe you might like substitution better. You know, Marjorie had a favorite name for this. You didn't call it substitution method. You called it, huh? U substitution. Is that what you said? Yeah, U substitution. So let U, since Marjorie likes you, she likes you. Okay, never mind. Okay. Let U equal, what do you say? Someone said 9y minus 5. Okay, then what always follows that? Oops, that's not a they, it's a then. Okay, ooh, that's ugly. All right. I'm having trouble writing today. Then du is equal to what? Not quite 9 dy, right? 9 dy. We really don't want a 9 dy, we just want a dy, so what might we do? Divide both sides by 9. So now we can, instead of dy, we'll put 1/9 du. Okay? So here our arc length is 1/2. And then we're going to pull out a 1/9 too, so that would be 1/18. Ooh, this is getting messy, isn't it? Okay. Because that 1/9 is coming out too, so it'll be 1/18. The integral, now I'm not going to put 1 to 5 anymore. Why? We're now in terms of u's, not in terms of y. So since it's going to be a du, and du was 1/9 dy, so that's why the 1/9 came out front. What is our limits now? What is our limits now? Okay. Whew. Well, let's just look here. When y is equal to 1, what's u? 4. And when y is equal to 5, what's u? Whoa, 40. Okay. And then what's our integral now? U to the 1/2. I think I can do that one, or at least some of you can, can't you? So S is equal to 1/18. What will that be? Antiderivative of U to the 1/2. U to the 3/2, is that what you said? Yeah, I thought so, okay. Times what? Not times, divided by 3/2, because you divide when you're integrating, you multiply when you're dividing, divide. So that would be the same as multiplying by 2/3, right? Dividing by 3/2 is multiplying by 2/3. I like to do it the easy way because I'm lazy, okay? Got it? Okay, and evaluate that from 4 to 40. This is not looking pleasant, is it? All right. One thing will happen, the 2 can go into the 18 9 times, so we're left with a 1/27. Okay, get out of there. Okay, now let's evaluate this one. I have a feeling I'm doing something wrong, but let's just carry it on out. I can't take the square root of 40, can I? So well, we kind of can. That would be the square root. The square root of 40 would be the same as 2 times the square root of 10. So let's leave it that way. And then we're going to cube that. And by the way, I've already gotten rid of the 3, so that's out of the picture too. The 3 and the 9 went together, so they're out of there. So don't worry about those anymore. Okay. So what did I say? 2 times root 10, and cube that. Did you have a question? Just hold me on that. What's the question? Oh.
Do we have to substitute 9y minus 5 back in?
Say that one more time.
Do we have to substitute 9y minus 5 back in?
Ultimately, but you see, by doing this, we won't have to. Okay. So if we had kept it in this form, okay, you're talking about, yeah, this. Okay. You see, with a definite interval, you don't have to do it. With indefinite interval, yeah, you have to back it off. And who knows, that might have been the better way to go here. I think we'd have been in the same problem though, because when you would have plugged in this, we still would have been taking the square root. You know. So I think we've been in the same boat. Let me just make sure I'm not heading us down. Oh yeah, it's a mess. Okay, here's how they leave it. They say 40 to the 3/2 minus, and then 4 to the 3/2 I can do, because the square root of 4 is 2, and that cubed is 8. Okay. That's how they wrote their answer. Okay. 1/27 times 40th to, well, they didn't either. They write 4 to the 3/2. But 4 to the 3/2 is 8, so I don't know why they didn't just write that. The typesetter just loved doing exponents, I guess, so I guess that's why they did it. And then they just did an approximation on that. Yeah, but that's the answer they get. Beautiful, though, isn't it? Someone do 40 to the 3/2 power. Got a handy dandy little calculator somewhere.
It's like 252.9.
Say again?
The whole thing, like 3/2 power, it's like 252.9.
What's in the parentheses? Is that right? Or just the,
Or just the first part, and then subtract 8.
and what?
Okay.
And then divide by 27. Is that what you're, or subtracting 8 and then divide by 27.
So 9.9.
9.073?
Yeah.
That's what the book got to. Good for them. Okay. All right. So, like I said, just to get these to work, you have to have some pretty weird formulas. And this was fairly weird, but it was doable. But then to get reasonable, I mean, easy to calculate answers, still not very easy. So, yeah, you got 40 to the 3/2, but what's that among friends? Okay. So that's example 3. Let's move on to 4. Any questions on 3 first? You okay with it? Any further questions? All right, let's move on to 4. And this one's at larsoncalculus.com, so if some of you don't have a book, you can at least go and see this example there. Find the arc length of the graph of y is equal to the log, one of my favorite functions of all time, of cosine of x. Okay? And we're going to do it from x equals 0 to x equal pi fourths. Okay. Now, why didn't we go to pi halves, you reckon? The cosine of pi halves is 0, and log of 0 is undefined. So that's why we didn't go to pi halves. We could have gone closer to pi halves, but pi fourths is fine. Okay? We're okay in that range there. Okay? Now, we're finding arc length. Okay? Now, they show this in the book, and I'm not sure I would have guessed this is what it looks like here. But this is this function here. Okay. There is that little portion there from 0 to pi halves. This is log of cosine x. Notice it's not defined as negative pi halves or positive pi halves, and it's negative everywhere here. Of course, that's true too, because cosine is never greater than 1. It can be 1, and then the log of 1 is 0, so it's right there. But everywhere else is negative. Okay? Cosine less than 1, and the log of a number less than 1 is negative. So that's negative. So are you fearful you might come up with a negative arc length? No, we're not. You don't worry about that. It's not going to happen. It's just that you're down there in the below the x-axis, but that doesn't make the arc length negative. All right. Now, where would you begin? Take a derivative. Y prime is equal to what? A little louder? a little, I can't hear. Negative sin x?
Yeah, negative 10x. That's what
Negative tan x, perfect, okay. It's 1 over cosine x, that's the first part. The derivative of the log is 1 over cosine x, times the derivative of the inside is a minus sine x. It's not 6, but sine x. And so this is negative tangent x, if you like tangents better than sines and cosines. Okay, so there's your derivative. What do we do with that derivative? Square it. So this derivative squared is going to be negative sine x, or tangent x squared, which is going to be tangent squared x. You lose the minus sign. Okay, and then what do you do with that? Add 1 to it. And does anyone happen to know what tangent squared x plus 1 is? Well, that's secant x, isn't it? Okay. That's secant squared x. Okay. Perfect. Okay. If that helps us any, I don't know that it does. And what do you do with that then? You take a square root of it, so now what we've got is the integral from, we're still in x's, aren't we? From 0 to pi fourths of, and we're taking the square root of this, and square root of secant squared x is secant x. Now, does anyone happen to remember what the antiderivative of secant x is? You can always look it up in a table. That would be legal in most states. Or you could, if you want to actually calculate it, which I know y'all do, 0 to pi fourths of, what is secant? 1 over cosine. So that would be cosine to the minus 1. Yeah, I'm not sure I'll take looking it up. Don't you? Okay. So let's go with looking it up. Okay. I can't remember. I think it's in the front of the book. Different books put them in different. There it is. Basic integration rules. Secant x. There it is, number 12. Front inside cover of the book. It's our favorite. Log of secant u plus tangent u plus c. Okay. So let's just go straight to that. It's the log of, now they put it in absolute value bars, but between 0 and pi fourths, guess what? All your trig functions are positive, so you don't need absolute value here. So log of secant x plus tangent x. You don't need the absolute value because both of those, and make sure I did it right. Yeah. Okay. And this is evaluated from 0 to pi fourths. Ooh. All right. Now, let's do the pi fourths first. What is secant of pi fourths? Square root of 2, is that what you said? You're absolutely right. Just leave it right there. Square root of 2. Because you see, it's the reciprocal of cosine. Cosine is root 2 over 2. And the reciprocal, that's the same as 1 over root 2. Reciprocal is root 2. So that's log of root 2 plus, and what's the tangent of pi fourths? 1, yes, very good. Okay. Now secant of 0 is 1. Okay. So minus log of 1, and what's tangent of 0? Second? 0. Okay. And what's log of 1? Second? 0. So this is 0. Okay, so there's your answer. Log of 1 plus root 2 or root 2 plus 1. And if you punch that in a calculator, what do you get approximately? Second? 0.881. That's what the book got to. Good for them. Okay. Make sense? All right, good deal. All right, number 5. As I said, these are some wonderful little functions that you can use this on, because some really simple little functions, you'll get things you may not be able to integrate at all, even with tables. All right, let's do example 5. An electric cable is hung between 2 towers that are 200 feet apart. Okay? Now I'm wondering if I need to draw the picture. Hopefully not. You can sort of picture that yourself. Okay? As shown in the figure. The cable takes the shape of a catenary, and the equation of that catenary is y is equal to, one of your favorite equations of all time, 75. Now that 75 comes from the fact, without drawing it, let me hold it up for you. They happen to put the y-axis exactly halfway between that. So the 75 is 1/2 of the 150. Wait. No, there's 200 feet apart. Sorry about that. Without any reason, they tell you it's 75. It's half of 150, but they don't go into any detail of why that's the case. Why it's 150 as well, but I guess the picture would be helpful. So let me draw the picture. Or I'm not going to draw the towers. I don't draw towers well. Okay. So this is going from minus 100 to positive 100. And you're starting see, I think they basically left something out. They must have meant what the height of the cables were to begin with. Well, they just said between 2 towers as shown in the figure. They don't tell you the height of the towers, but they do tell you the height where the catenary comes down, and that is 150. So that's just part of the problem. This is 150. So the towers are, I'm just going to draw poles because I don't draw towers well. Here's a pole here, and here's a pole there. I don't know why I put a light on the top. It doesn't need one. So anyway, it's hanging down like that. Okay? And the dip in the catenary, which is the lowest point, is right there at the y-axis. My picture doesn't show it, but theirs does. Okay. Now they give you the equation for that catenary, and that's 75 times e to the x over 150 plus e to the minus x over 150. Okay. Now, they also give you a sort of a shorthand thing, and this is the same as 150 times the hyperbolic cosine of x over 150. Now, this is more than just a casual question. Do y'all deal with hyperbolic cosines? I've never found anyone who does. And yet math books love to do them. But when you did Cal 1, did you ever do the transcendental functions or anything? I see no reason. To me, those are far easier to deal with, exponential functions. And that's how it's defined. So why introduce that, and then you have to keep up with what's the derivative of that and stuff like this? Well, I can do a derivative of an exponential function without any struggle at all. So why they even introduce them, I don't know. I thought maybe there's some major out there who uses them all the time, and then I wanted to apologize. I said I think they're totally worthless, but so far I haven't found that major. So maybe there are people who use them, but I haven't found them yet. Okay. So find the arc length of the cable between those two towers who have that formula. Okay? So what would be the first thing you would do? I've been answering that question well so far. Take a derivative, of course. Have I told you my little saying about that? Probably not. Well, I know probably Bill has heard it, and Jake, okay. In Cal 1, anyway, usually when someone asks a question, okay, what's your first step? It's usually going to be take a derivative. I mean, Cal 1, that's almost that way in Cal 2 a lot, too. I make the analogy of that to, I don't know if any of you, go to church or if you just do this, but a lot of churches will have children's church, right? And in children's church, they bring all the little kiddies to the front of the room and then front of the sanctuary there, and then usually a pastor or some of the really important persons is down there, and they always like to start off with a question. So they always ask a question. Of course, the kids are not wanting to say anything. So finally, some little boy in the back will say, "Jesus." Why? Because that's going to be a good answer in most churches, right? It's a question. Jesus is never a bad answer, is it? Not in church. So I call this your Jesus answer. So I say, what's your next step? Jesus' answer in Cal 1 and lots of Cal 2 is take a derivative. So that's usually going to be a good first step. So there's your good Jesus answer. So what is this? Let's do it. Is it helpful to multiply the 75 through or just pull it on the outside? Which way you want to do it? I don't care. Which way? Outside. Okay, leave 75 outside. Okay, take the derivative of the inside. What's the first one going to be? Not too bad. It's what? E to the x over 150 times, chain rule, anybody? Derivative of x over 150. So that was a 3x. What's the derivative of 3x? 3, okay? So derivative of 150 times x would be 1 over 150. Okay, good deal. Next. A little louder. Huh? Negative 1 over 150 e to the minus x over 150. Now, if you were big into hyperbolics, that's similar to a hyperbolic sign, so, but who cares? Well, here we see 75 is exactly half of 150, so this could be a 2 and that could be a 2. That makes things a little nicer. So we got our y prime is equal to 1/2 of e to the x over 150 minus e to the minus x over 150. Okay, now what do we do with that? Square it. Okay, so that will be y prime squared would be, what would that be? 1/4, I like that, times, now we're squaring a binomial, just like any old binomial we square. Square the first term, which is e to, then when you're squaring an exponent, you're squaring a number with an exponent, you double it. So that would be x over 75, wouldn't it? Okay, without that in the way. Okay, there's the first, squared the first term. What next? Twice the product of the 2. So that would be a minus 2. And what's e to the x over 150 times e to the minus x over 150? keep the e, the base, add the exponents. 0, e to the 0 is 1, so it just is a minus 2. Okay? That wasn't too bad, was it? And then you have square the last, which would be a plus, get out of there, e to the minus x over 75. I believe that's right. Right? Any disagreements? Now what do we do with it now? Add a 1 to that. Before I do that, let's multiply through our 1/4. Is that okay? That would be 1/4 e to the x over 75 minus, what would that be? 1/4 times 2? 1/2 plus 1/4 e to the minus x over 75. Right? Except I don't want a parentheses there, because I'm going to add 1 to it. Now what will this give us? 1/4 e to the x over 75 minus 1/2 plus 1 would be plus 1/2 plus 1/4 e to the minus x over 75. Okay? So we've added 1. Now we need to do what? Take a square root. So let's take a square root of this thing. Okay? Now, would I be forgiven if I make this 2 over 4? Is that all right in most states? Okay. So now I got common denominator of 4, so let's take out a 1/2, right? Square root of, okay. So that would give 1/2 times the square root of x to the, e to the x over 75 plus 2 plus e to the minus x over 75. Now, I don't know if you remember back one of the examples we did last time. When we started with something, squared it and added and then, and then wound up with something that looked awfully close, except maybe just a minus sign off. And since this was the perfect square of that, with the minus sign in here, don't you see that this should be the perfect square of this, except with the plus sign in? Would that be too big of a showgun? Huh? Yes, it is, isn't it? So let's just write this with a plus sign on it, and that would be our square root. And that's what we're going to integrate, isn't it? Okay? So we're doing the s, the arc length, is equal to the integral from, I'm not going to do this either. Isn't that, if I had drawn this correctly, isn't this arc length from here to here, shouldn't that be exactly the same as that arc length from there to there? So let's just do 2 times x 0 to 100, right? So let's make it 2, 0, well, 0 to 100. And let's see, we have this 1/2 from here, don't we? I almost forgot that. It's going to wipe out my 2. Shucks. Okay, I'll just have a 1 out there. Okay, and we said that's the perfect square of e to the x over 150 plus e to the minus x over 150 dx. All right. Now, if it's all right, I think I'll erase the Twin Towers, even though that would mess up the final book of Oh, why am I going blank on the name? Tolkien's Lord of the Rings. Okay. Wiped out the Twin Towers here. Okay. Wasn't that the last book? Okay. Y'all should know your literature to be in the calculus class. Okay. Even if it is popular literature. Okay. All right. Let's get rid of as much of this as... Oh, that was a minus on it. Wasn't a tick mark? Okay. I don't know what that was, but whatever. We'll erase that too. Okay. I think that was all right. Whew. Okay. Now what's the integral of that? S is equal to antiderivative of e to the x over 150. I know it's got an e to the x over 150 in it, right? Would you buy that? Okay. What goes in front of it, though? $150. You undo a chain rule. Chain rule, you would be multiplying by, or dividing by, you're multiplying by 1 over 150. This time you multiply by 150 over 1. Okay. And how you can check that is just take a derivative of it. And derivative of this would be e to the x over 150 times 1 over 150. 1 over 150 goes out, and that leaves you out. Just exactly that. All right. So that was okay. And then the next part would be minus 150 e to the minus x over 150, if I could get my pen to write, and we're going to evaluate that from x going from 0 to 100. When I get too much writing on the screen, it takes a long time for it to write. Okay. Now this is a mess. Okay. It doesn't write, and then it writes twice. Okay. Now let's evaluate that at 100. Okay. That would be 150 e to the 2/3, right? Minus 150 e to the minus 2/3. You can't throw away your zeros here, because that would be minus a 150 e to the 0, which is 1. So it's minus 150, but then the next one would be a minus, which is a plus 150. So you can throw them away after all, okay? It just happened. So I think that's your answer. And perhaps they pull out the 150. 150 times e to the 2/3 minus e to the minus 2/3. I don't know if you can read my writing. Okay. It sure is slow. Okay. Let's see what they got. 150 times e to the 2/3 minus e to the minus 2/3. And they do a little calculation there. Anyone do that? About 215 feet. Perfect, perfect, perfect. All right, good deal. Any questions on that? 10 of those on a test would be really good, wouldn't they? Let's move on. Okay. Area of a surface of revolution. Another, what are we calling this? Well, no. We've been doing arc lengths. The second half of this, or part of this, is surfaces of revolution. So that's what we're going to do now. Area of a surface of revolution. Now, Anyone at least want to give me a, whoops, going backwards, a conceptual idea of how this might work? We're doing an area of a surface of revolution. Remember, we had an old curve here, and we used to do disk methods or shell methods or something to do volumes of it. Now we want to do the area of this, when you revolve that curve around the axis. Okay? Well, wouldn't that be taking the arc length and doing the 2 pi r of that? That looks like that should work, doesn't it? Well, let's see if that's what happens. So the definition of a surface of revolution, when a graph of a continuous function, needs to be continuous of course, revolved around the line, wherever the line is, vertical, horizontal, whatever, the resulting surface is called, amazing, a surface of revolution. Okay? The area of a surface of revolution is derived from the formula for the lateral surface area of the frustum of a right circular cone. Yes, I remember that so well. Okay. To me, to bring all this into it, it's almost muddying waters that I think you could do so much easier by just doing arc lengths. But they do this. Consider the line segment in the figure below, that right there, that L, where L is the length of the line segment, good for them. R1 is the smaller radius of the frustum of a cone. This is just a slice of a cone. That's what we mean by frustum. And R2 is the larger radius of the frustum of the cone. Now, they say right end and left end. I like to think large and small. It doesn't really matter. Okay. Now, and then you're going to revolve that around an axis of revolution, wherever that happens to be, because your R's are measured from the axis. Okay, that's going to be pictorially what your surface of revolution is. Okay, when the line segment is revolved about its axis of revolution, it forms the frustum of a right circular cone with the surface area. Yes, we remember this, 2 pi r times L. Okay? Well, 2 pi r is the, what is r? R is the average radius of the two. So basically, let's go back here and take the midpoint here and get that radius and revolve that around here, 2 pi r times that length L. Now, that's not quite the same as saying of the cylinder here, because then your L would be less, okay? But it's taking the average radius there, and that does give you the correct answer, okay? Take your word for it, okay? Where R is the average radius of those two, okay? Now, consider the function f that has a continuous derivative of an interval on an interval a to b, oh, here it is, a to b. This is the curve, okay? Function f is equal to f of x, okay? And it's continuous derivative. Not just that the function is continuous, it has a continuous derivative, which is important too. And that's why, remember, we kind of failed on that one, that didn't have a continuous derivative at one endpoint. So we had to split things up. The graph of f is revolved about the x-axis. Okay, we're doing it around here to form the surface of revolution, as shown here. And every band here can be approximated as a frustum of a cone. Different cones all the way around there. So, frankly, why think of it that way? Think of that incremental arc length here. You do that around it. It's the same concept, only it leaves out a whole bunch of mess, like the average radius and that kind of stuff. But anyway, we'll live with it their way. So the radius is going to be the function value, average function value here, okay? And the L is going to be, what is that? That's Pythagorean theorem. We used Pythagorean theorem when we did arc length. So we're going back to arc length, okay? without having to do frustums of cones, but we'll do frustums of cones. Let del E or delta or whatever you want to call it, a partition in AB with the subintervals of width delta x of I, then the line segment of length delta L sub I would be, there's that good old Pythagorean theorem, the square root of delta x squared sub I squared plus delta y sub I squared generates a frustum of a cone, good for it, and R sub I be the average radius of that frustum, that's what we did before. By the intermediate value theorem, a point D sub I exists in the ith subinterval such that this radius is exactly equal to f of that D. Okay? Now that is bringing sort of a new twist to it here, and it's hard to see there. So rather than taking the midpoint here, you're basically, and they did this one that's so close it doesn't matter, but if you had a lot of difference going in there, you would have the D to be the one that's right on that curve. Okay, so that's the same as that curve. So that gets you a little bit better than just taking an average. There is an R sub I, some radius R sub I, such that you're exactly equal to that f of D. The lateral surface area, and it really doesn't matter because you're going to let your delta, your partition get infinitely small, so it's all going to be the same. So the lateral surface area, delta S sub I, is 2 pi R1 times the delta L sub I. Okay, hopefully you see this is coming out to be the same thing I was talking about. 2 pi, the R is the F of I, or F of D sub I, okay? And this L was the Pythagorean theorem. So it's 2 pi F sub D sub I times, and then when you divide by delta x squared, both of these by delta x squared, and multiply by delta x squared, that gives you delta x out here, this here. What do we have? 2 pi times the F, that's the radius, times the arc length. So why goes a frustum of a cone 2 pi times the radius times the arc length? Because this right here is exactly what our arc length turns out to be. Now maybe there's a reason mathematically and theoretical thing you can't just make a jump like that, but we're going to make jumps anyway as we take limits and stuff. So why not just jump to that and not even think of frustums of cone, but just think of 2 pi times that radius of that thing, the F of D, times that arc length. That's what you're revolving around there. To me, that makes perfect sense to do it that way. The total surface area is approximated by that, of course, and then we'll change the limit. As n goes to infinity, your delta x going to 0, this will then give you your integral. And that will be this. The surface area will be 2 pi times the radius, which is this is going from the x-axis, the f of x is that, times the arc length, that little segment there, dx. So, yeah, that's the incremental arc length that gives it to you. Okay? Now, in a similar manner, if the graph of f is revolved around the y-axis, then the s would be, now here's the interesting thing. They don't switch to be y's here. They say now the radius is x, and that incremental part is still that. You know, it's just sort of hopping around this way. So rather than f of x here, it's just x down here. And that makes it even easier. You don't have to change things to there. If it's helpful to, go on and change them. And if you change to f of y's, then you have an f of y here, not x. Okay? If this function was one that was really nasty, trying to take a derivative of it with respect to x, then change to y and do the limits to y, c to d or whatever, but then this becomes an f of y there, not an x. So this is much easier to do this way. In fact, Usually it's easier to integrate than that is. Well, I don't want to say usually. It can be. Okay. In these two formulas for S, you can regard the products of 2 pi f of x, or 2 pi x, as the circumferences of the circle traced around the point xy. That's exactly what it seems to be on the graph revolved around the x or the y-axis. And in one case, the radius is r is f of x, in the other case, r is x. So if you're doing this function around the x-axis, it's f of x, 2 pi f of x, that's your radius, that's what's revolving around here, times the, basically your arc length part of it, square root of 1 plus f prime squared, just like we did before dx. If you're revolving around this way, your radius is now x, not f of x. This is the radius this way, this is the radius this way, but your arc length is still the same in terms of x's. Now, if it's nasty that way and you need to take it in terms of y, then you make this y f of x, yeah, f of y there. So you have to change everything around. Usually that's better to leave it like that. So here's the definition. We just kind of derived it, now we go back and tell us this. Let y is equal to f of x have a continuous derivative on the interval a to b. The area S of the surface revolution formed by revolving the graph of f about a horizontal or a vertical axis. Horizontal axis would be this one, if y is equal to f of x. 2 pi times the integral from a to b. Those are limits on x. R of x, which is your f of x. I don't know why they went back to being r. There's no reason. Why is that not f? Oh, okay. Sorry. Because of this. They say a horizontal or a vertical axis. Not necessarily the x-axis anymore. So this r of x is now some function. If you're doing about x equal negative 3, I mean y is equal to negative 3 down there, a horizontal axis down here, then your radius function will be your f of x plus 3. Okay? So minus 3. So that's why they put r of x there, because you have to adjust this. If it's the x-axis, that would be the f of x. Okay? And then this is your arc length part. Doesn't matter. That doesn't change. Okay? That part there. Okay? It's just your radius part changes. Now, if r is equal to g of y on an interval c to d, then now, in this case, they're changing, because they're not doing around the y-axis now, they're doing by any other old axis here. And if that's the case, then you have to have the r as a function of y, because you see this line here is a function of y. So now you go back to the other case where you do change the x to a function of y, and that then is what is incorporated here to give the r of y. G of y, g prime of y, that's still the same. Where r is the distance between the graph of g and the axis of revolution. It's like, we'll see. Now, a lot of blah, 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 right? Let's actually work it. Okay. Here is example 6, which is top of page 480, if you've got a book. Find the area of the surface formed by revolving the graph of y is, or f of x is equal to x cubed, and they've drawn that in there. Okay. On the interval from 0 to 1, so you don't have the part down here, 0 to 1, okay. About the x-axis, as shown in this figure, okay. That goes back to a fairly simple one, relatively speaking. So what is the area of the surface? S is equal to, this is, little s is arc length, capital S is surface, okay. What would that be? Okay, certain your limits are from 0 to 1. So obviously using, or at least I think you're using dx. Because they're also 0 to 1 dy, but I don't think you want to go that direction. 3 is in dx in. Limit 0 to 1. Notice I left some space here, Thomas. 2 pi, yes. Let's get that 2 pi out there. Okay. Now, what we're describing here is a little segment here, little s here. This little segment of your arc length here is revolving around the x-axis. So what is your radius there? That's your x, alpha of x, which is x cubed. And then what goes, that's the r part, 2 pi r times ds. That's how I look at it anyway. So that's the square root of 1 plus, okay, you got to go through all your things you did with arc length. What's the first thing you do? F prime of x is equal to 3x squared. Okay, and what do you do with that? Square it, and that becomes 9x to the 4th. And what do you do with that? Plus 1. And then you take a square root of that, and that gives you the rest of it. So there's your, okay. That is your, what's inside the integral. So there's your plus 1. We already got there. And this will be a 9x to the 4th. And then you have your dx. Oh, I already have my dx out there. Okay, I don't think I've left anything out. I was doing it in so many different pieces. I believe we got it all there. Now, how would you go about integrating that? He's getting tired again, isn't he? Second? Oh, yes, let's substitute again, okay? What do you want to substitute? U equal, say again, 9x to the 4th? Why not include the 1 with it? Just for funsies. Okay? How about 1 plus 9x to the 4th? Okay? And what does that give you? Then, what's the next step? du is equal to 36x to the 3rd power times dx. Perfect. Well, I sure don't want a 36x cubed dx, but I do want the x cubed part. So let's divide both of those by 36. Okay. So now my integral is going to be 236, which is 1/18 pi, so pi over 18, times the integral. And we won't do the limits quite yet, but I believe that's going to be u to the 1/2 du on it. So this was our u, that's exactly that, and the du was this, divided by 36, so that's that. I think we're covered. But we still got to figure out what the limits are. So when x was 0, what was our u? 1. When x was 1, what was our u? 10. Okay. So now we've even got the limits there. Okay. So this will be pi 18ths. And what's the antiderivative of u to the 1/2? Anybody? U to the... You're taking a derivative, aren't you? Antiderivative. 3 halves times what? 2/3. Okay. Seems like we've been there before. I don't know why. There it comes. We'll evaluate that from 1 to 10. Okay. Now let's see what we get. Well, here we go. All right. I'll go 2 into 9, 18 will be 9, so this is going to be pi 27ths. This is looking an awful lot close to what we had before. Times, see, I pulled the 3 out, so that's taken care of now. 10 to the 3 halves minus 1. Now that's what I got. They did pi 27ths, 10 to the 3 halves minus 1. So if you got a handy dandy calculator, punch away and see what you get. The 3 halves power of 10. 10 is just a little bit more than 3 squared, so that would be close to 30 probably. Pi, the 10 pi ninths or something like that. 10 ninths pi. Maybe something around 4 or so.
3.56.
Oh, that's close enough to 4. 3.563 is what the book had. All right, good for them. Any questions on that? Pretty exciting stuff, isn't it? Okay. Okay. Now, there's examples. Oh, this is example 6. Okay. Let's see how they did. Did y'all need that up there a little longer? No? Good. Okay. So, the distance between the x-axis and the graph is just your function. Okay, so your r of x is your f of x. And because f prime is 3 halves 3x squared, okay, I remember what the function was. Yeah, okay, I remember now. The surface area is that, 2 pi, there was that, integral from a to b, that was 0 to 1. The r of x is your f of x, which is x cubed, times the square root of 1 plus 9 x to the 4th dx. Okay? Well, there's a formula for the surface area. When you plug in our values, you get that. 2 pi 0 to integral 0 to 1 x cubed plus times square root of 1 plus 3x squared dx, which would be that. Now, here's how the book likes to do their substitution. They like to look into the crystal ball and see what they want it to be, and then take care of that. Well, they're looking in here and saying they're wanting the derivative of this to be 36, so let's make this 36x cubed here, and that means bring a 36 out here, which is sort of the same way we did, except we did it with the u's and du's, but they haven't even gotten to the u's and du's yet. But they know that's where they're going to want to go. So this is pi 18ths, which is what we had, and they didn't do a substitution. They went straight to knowing this was derivative of that, then, yeah. Without the substitution, they did it. Now, I put 2/3, they did divided by 3 halves. So they eliminated the u stage and everything else there. And when you plug all that in, you still get the same answer. So it works quite nicely. They sure skip a lot of steps in getting there, in my mind anyway. You okay with it? Same thing we got. Okay. Oh, and that was that. Okay. Now, they skip example 7. So let's just do example 7. Find the area of the surface formed by revolving the graph of f of x equal x squared on the interval from 0 to 2, 0 to root 2, I can't read, about the y-axis okay, as shown in the figure. Okay, when I do a figure, I'll try to do a quick one of that. Y is equal to x squared, our good old favorite parabola here, but we're only going the 0, there's 1, and root 2 is 1.4, so that would be about right there, and this would be a value of 2 here. Okay. So we're doing the bowl that you get from revolving that around there. Okay. So now, I did say about the y-axis, right? Okay, how would you proceed here? Second, okay, I think there will be a 2 pi. So S is equal to 2 pi. And I'll go from what? Okay. Okay. So as soon as she said that, 0 to root 2, I know she's doing a dx. Because the y's are going 0 to 2. The x is going 0 to root 2. Okay, I'm with you here. Next. Yes, times x. Because your radius in this case is going to be just your x. Okay, that's what this little segment is going around that radius, and that radius is x. And what goes next? The square root of. Yeah, we're going to do a derivative. Okay, let's do it. What derivative were you talking about? F prime of x is 2x. What do we do with that? Square it, and so that becomes 4x squared. And what do we do with that? Add 1 to it, and then take the square root of that. Okay, so I'm going to write it like we usually do, 1 plus 4x squared dx. Now, think we got everything covered. There'll be a 2 pi. Now, how do you want to approach that one? Could do it the way the book did if you prefer doing it that way, or substitution. Okay. What would you substitute? Let x equal what? What did you say? I couldn't hear. 1 plus 4x squared. Is that what I heard? Then oh, that's u equal that. X can't be equal to that. Okay. Du is equal to 8x. Is that right? Dx. Don't forget the dx. I don't know why the bar didn't come down, but I'll put another one in there. Okay? But we don't really want an ax dx. We just want an x dx, so we'll divide both sides by 8. Which then means we will be dividing this by 8, which makes this 1 over 4. Okay? Integral. Oh, we got to change our limits too now, don't we? What are our changes of limits? When x equals 0, u is equal to 1. When x equals root 2, 9. I kind of like the sound of that, okay? And your x dx was divided by 8 was your du, so there's your du part. And then you have u to the 1/2. Pretty familiar looking integrand, isn't it? So this will be 1/4 or pi fourths antiderivative of u to the 1/2 2/3 to the 3/2 power, and we'll evaluate that from 1 to 9. This one's even easier to evaluate because those are both perfect squares. Okay? So the square root of 9 is 3 cubed is, wait, before we do that, let's make this a 2 times 3 would be 6, pi 6 out front. So let me write that, pi 6, that will just take all the numbers out of the picture. Okay? Those numbers anyway. And this will be, what do we say, 27 minus, say again, 1. So that would be 26. So that would be 13 pi over 2. Yeah. Let's see how the book did. Oh, look at that. They got 13/2 pi. No, thirds pi. How did I do that? Oh, yeah. I divided by 2. Yeah, that's 13/3 pi. 26/6 is 13/3. Okay. Now, what makes this especially easy, those are awful close to each other. This is a little bit more than 13. How much more than 13? 0.614. Okay. So that's pretty reasonable to assume. Any questions on that? Is it too many? Yeah.
I have one. I keep missing this step. I'm pretty sure it's pretty easy, but when you're finding the integral, so we started out finding the integral from 0 to the root 2. How do we know to change it to 1 and 9?
Okay. Because you're changing this. This is good for x's. When you change the u, you've got to change for u's. So what we do, here's where we change x's to u's, right? So we take the 0 from here, plug it in here, that's where you get your 1. Okay? So that's u is 1. Then you take the x equal pi halves, plug it in here, and pi half squared, where is that? Root 2 squared is 2 times 4 is 8 plus 1 is 9.
Okay.
Yeah, that's where it was. Good question. Excellent question. I start doing things really fast, especially if someone says a right answer or something that sounds like a right answer. I jump right on it, and we just go. Okay, so be sure to ask. Any others? Good questions. All right. That then finished 7.4. So I'll actually, anyone need that a little longer to look at? I know you did. You enjoy it so much. Okay, 7.4 homework exercises. Do number 5 is the Calc Chat. I've given some of these before. 7 or 9, but both the Calc Chat. 7's a Calc View. Any of the odds 11 through 19, they're all at Calc Chat. Any of the odds 21 to 29. Now they say you need a graphing utility. I don't think you really do, but see it. I mean, try it without. And that's any of those are at Calc Chat. Okay. Then 31 should be a Calc Chat. 33 is just like the example we just did a little bit ago with the twin towers. Okay. 35 will be somewhat similar to that. Only it's upside down. Okay. 37, somewhat similar. Then any of the odds 39 to 43, they're all at Calc Chat. 39's at Calc View. Either 45 or 47, they're both at Calc Chat. 45's at Calc View. 49 should be at Calc Chat. You can explore doing either 51 or 53 if you'd like. They're both at Calc Chat. You can think about doing 55 if you'd like. That's at Calc Chat. You can choose any of the odds 57 through either 57 or 59. They should both be at Calc Chat. There's a modeling data at 61. They say you need graphing utility, but see if you do. 65 should be at Calc Chat. 63 is a volume and surface. And then approximating arc length or surface area, either 65 or 67, if you would like. 69 is another suspension bridge, similar to what we did earlier. That's at Calc Chat, and 71 is another arc length and area at Calc Chat. Okay. This wraps up 7.4. Any questions on 7.4? All right. Somewhere here. I've lost my... don't know why that disappeared on me. Got to go back to this. And this is 7.5. All right, we are not quite, almost 2 hours into it. Y'all want to take a break? Things have gotten awfully quiet, and I'm yawning some, so I wouldn't mind getting up and moving about. So why not, as soon as we get this come up, let's take a break. Keep it no more than 5 if you can help it. Last time I took a break in the middle of a class, someone stopped me in the hall and I had to deal with some sort of emergency. So hopefully this won't happen this time. So we'll start there, but I'm going to pause this. Otherwise the poor people at home won't know what we're talking about. All right, so we're continuing Chapter 7, Applications of Integration. And this time we're going to do some work. Okay, so 7.5 is work. Okay? We'll find work done by a constant force, which is pretty much a piece of cake. And I shouldn't say that because I haven't had lunch. And then we'll find work done by variable forces, which can be a little more, but they're usually not too bad. So let's do work by a constant force. In general, work is done. Any of you had physics yet? Okay, most of you have. Okay, what definition of work? Simple one. Yes, force times the distance. Okay, that's it. When you're moving something, general work is done by a force when it moves an object a given distance. Okay? If the force is applied to the object, if the force applied to the object is constant force, then the definition of work is pretty straightforward. The work done by a constant force, if an object is moved a distance d in the direction of an applied constant force F, then the work done W, capital W by the way, little w is usually weight, capital W is work, done by the force is W is equal FD. Now most of the time force is capitalized too. Most of the time D I see is lowercase d in most physics books rather than capital D, but it doesn't really matter. You can make it capital if you want to. Because usually in a math book, capital D stands for the derivative operator. So I'm so surprised they do a capital D here because this is a math book. But anyway, force times the displacement, if it's a constant force. Pretty straightforward. Okay? Now, surprised to go into this, but it's worth, more physics and math. 4 fundamental types of forces that we know about anyway. Gravitational force, electromagnetic forces, strong nuclear forces, and weak nuclear forces. Now, I don't know why they put them in that order. If I were ordering these, I would have flipped those last 2 around. Anyone know what those are? Of course, gravitational forces. Any force between 2 bodies of any 2 masses. Of course, they have to be pretty massive bodies before you can measure them because the coefficient, coefficient, universal gravitational constant is 10 to the minus 11 or something like that. They have to be pretty big masses before you can measure that gravitational attraction. Electromagnetic forces The formula is very, very similar, but of course you're dealing with different things, coulombs and distances rather than masses and distances, and those are completely different objects, but still Coulomb's constant, something like 10 to the 9th rather than 10 to the minus 11. So these are typically stronger, but they don't go nearly as far. It's rather bizarre. They're stronger on short distances, but they just don't have any distance that you deal with, okay? But that's why you see the experiment of combing hair, if you had hair, with rubberized comb or something, get the electrostatic forces, then pick up little pieces of paper. Have you seen that experiment? Never have. Okay. You haven't lived. Okay, so it can be done, and what it shows is, even though gravity's pulling that paper down, the electrostatic forces are pulling it up. So electrostatic forces are indeed stronger, but do it from here. No, you won't do it from a long distance. Now, I can't really go into too much about the difference between weak nuclear and strong nuclear, but these are nuclear forces, meaning inside the nucleus of an atom, which is incredibly, incredibly tiny distances, okay? And so within there, if you think about it, electromagnetic forces should be really powerful, greater in general, especially on short distance than gravitational. But think about what's in the nucleus of an atom. What's in there? What lives in there? Protons and neutrons. What charges are protons? Positive. Neutrons? Neutral. No charge at all. So here you've got a bunch of positive particles in there in an incredibly, incredibly tiny space, very, very close to each other. And what do positive charges do to each other? Electromagnetically? They repel. Well, what in the world is holding that nucleus together? These nuclear forces. These are incredibly stronger than electromagnetic forces, but they go through very short distances. Incredibly short distances. Y'all ever heard of angstroms? Probably not. Yeah, Bill has. Yeah, okay. That's what you used to measure atomic distances is. The nuclear distances would be incredibly small and even angstrom terms. So those are your forces. They go up in strength, especially if we reverse these two, as mentioned here, but their reach is much less as you go there. Force, why they put that in, I'm not sure. Did way too much on it. Force can be thought of as a push or a pull. I remember my 9th grade physical science teacher was the football coach, Julio Hubert. He played at Alabama well before Bear Bryant was ever at Alabama, but he sounded just like Bear Bryant. A force is a push or a pull. I mean, he just had this, and he scared the daylights out of everybody. He retired in a few years, which is good. But it's a force is a push or a pull. It changes the state of rest or the state of motion of the body, meaning it changes the momentum of the body, the velocity of the body. For gravitational forces on Earth, it is common to use units of measure corresponding to weight. Well, forces are weight, so yeah, that would be common. So forces and weight, same units. Newtons in the SI system, pounds in the U.S. customary system. Don't know why they did so much physics here, but that's fine. So let's do example 1. I guess I had to do something before they got to the first example. Determine the work done by lifting a 50-pound object 4 feet. Need a picture, or can you picture that okay? All right, good, okay.
We have to convert
From what to what?
pounds and kilograms or each the meters.
Okay. I'm all in favor of not doing it, but if you wanted to, you certainly could.
You just put pounds on this.
Yeah, just put the unit's going to be foot-pounds. And how many would it be? 200 foot-pounds. Let me get my pen back. So force is equal to, work is equal to force times displacement. I don't know what I was thinking. going back, I taught physics last night, and we were still in. So work is equal to force times displacement. I like little d, they like big D. Okay, work is the force of 50 pounds. Now, how do you get the 50 pounds? Well, what you're having to overcome is the weight due to gravity, the force due to gravity, which is weight, which is your 50 pounds. So it means you're going to have to exert a force of at least 50 pounds upward to move it. And it says lifting, so that's upward, 4 feet. So 50 pounds times 4 feet. And the unit for work in the U.S. customary system is foot-pounds. Now, have any of you ever used a wrench that was calibrated in foot-pounds? You haven't. Ever heard the term torque? What units do you use for torque? Foot-pounds. Are you measuring work? No. Okay. What you're measuring with a torque wrench is torque, which is a vector quantity. Work is a scalar quantity. And one of the reasons I put a dot in there is literally the dot product between two vectors. Force is a vector, displacement is a vector. Have y'all done dot product show? Yeah, you know. You have a dot product. When you multiply two vectors with dot products, you get a scalar answer. Work is a scalar number. No direction involved. It's just work. How much work you do. That's a dot product. With a torque wrench, that's a vector, cross product. When you do a cross product with two vectors, you get a vector. So torque is a vector quantity, also measured, and it's a force times the displacement. Now here's the difference. Work, and let's go back to a little phrase here. When an object is moved a distance in the direction of an applied constant force, that gives you work. I can exert a force on the chair downward. I'm not moving it at all, so I'm not doing any work. I'm grunting and my arm's shaking and stuff like that, but I'm not doing any work because I'm not moving at a distance. To do work, I do push in that direction and it moves in that direction. Force times displacement, that is work. If I did a force here, I can also move it, but notice it doesn't move quite as far because you see this force has both a vertical component and a horizontal component. The only component doing work on the chair is the horizontal component, not the vertical component. The vertical component is doing the work. Okay. Now, let's go to this, not taking up class time for this. Torque, on the other hand, what you do is torque wrench. You've heard of that, right? Okay. The object there, the nut that's frozen, whatever it is, or that I'm trying to tighten or something, is there. The distance I'm talking about is the length of the wrench. The force is going to be this direction. Notice there? The force is here, the displacement there, perpendicular to it. And when you do a force times the displacement, you get a vector quantity, right-hand rule, perpendicular to both of those. So if you add a torque wrench, that's not work. Even though it's measured in foot-pounds, still the displacement, still a force, but it's not work, it's torque. That's why those are different. All right, let's see how that was probably way more than you wanted to have, but there's no extra charge for it. Okay, so, here's a nice picture, isn't it? The magnitude required of force is the weight of the object, because you have to exceed the weight of the object before you can lift it, okay? So 50-pound force upward, and going up 4 feet, that would be 200 foot-pounds, okay? So the work done, that is work is equal force times displacement. They like capital D, 50 times 4. I don't like to write the numbers without the units, because units are your friends. You ought to keep up with them. Make sure they give you the right units, 200 foot-pounds, perfect units for work in the U.S. customary system. What's the unit of work in the SI system? Anyone know that one? Say again? I thought I heard someone say it. A Newton meter is exactly right, but that has its own name. A joule, exactly. Okay. Named after James Prescott, joule. Okay. Interesting story there, too. In the U.S. measurement system, work is typically expressed in foot-pounds. If you do very little, that would be inch-pounds, or a whole lot, that would be foot-tons, or something like that. You can use any force times displacement. Only they write it displacement times. In the SI units, or the International System Units, this comes from the French, who usually put their adjective after the noun. System international, system international, or something like that. The basic unit. A force is the Newton, named after Sir Isaac, and the force required to produce an acceleration of 1 meter per second, 1 meter per second squared, on a mass of 1 kilogram. We deal with masses here. In this system, work is typically expressed in Newton meters, also called joules. Exactly. Perfect. Joules named after James Prescott joule, as opposed to Isaac Newton. So therefore, Newton and joules are both capitalized, not the name. It seems like the name should be. The symbol is capital N, capital J, but meter would be small m. Okay, pounds, not named after anybody, so that's small. 2 feet, not named after anyone. Okay. In another system, the centimeter gram second system, CGS system, very seldom people talk about this anymore, but they used to be a big deal. Back when I took physics, part of the agony of it was having to convert between what they call MTS, meter kilogram second system, nowadays we call SI units, to CGS. You were just having to do this all the time. It's just an enormous exercise. Okay. The basic unit is the dyne. It's the force, and the displacement was in centimeters, and then the work was measured in ergs. Okay. The only way I really remember that well is my brother came home from college, and he had his physics before I went, and evidently his physics professor had given this story. If this is a centimeter, then what's this? It's an erg. It's a dyne centimeter. So that's the only way I remember that an erg is a dyne centimeter, because of that dumb joke. But I guess that's why they told it. Okay. You don't need it. Okay. But they give them here. Okay. The table below summarizes the units of measures. Yeah. I can't believe a math book is doing this. U.S. System, work is foot-pounds, force is pounds. Why didn't they do it in the other order? And the standard for the U.S. system, feet, pounds, and foot-pounds. SI system, meter, Newton meter, which is a joule. Notice these two are capitalized. And CGS, which hardly anyone uses anymore, is centimeter, dyne. And notice, don't use it much, doesn't have a single letter. You almost spell the word. And erg. Here's the other way I remember erg. Work is equivalent to energy. You measure energy in foot-pounds, you measure energy in joules, and the middle 3 letters in energy is erg. Okay, so that's another way to remember that. And that's the CGS system that hardly anyone uses. Here's some conversions if you ever need them. Foot-pounds to joules. And that notice joules to ergs is just the order of magnitude. Pretty big order of magnitude, because I don't want to get into this too much. A Newton is a kilogram meter per second squared. A dyne is a centimeter gram per second squared. So you have the kilogram to gram, that's 3 orders of power, but then you have orders of magnitude. Then you have centimeters to meters, which are 2 each, where the squares are 4. So you get so many different units in, so that's where the 3 times 4 is 7. So 10 to the 7th comes out there. And then you go the other way from this to this. Those are reciprocals of each other, I think you'll see. And a Newton is 10 to the 5th dynes, as opposed to a joule being 10 to the 7th ergs. Because you're multiplying again by a power of 2 here, but 10 to the minus 2, so that drops. It's nuts, okay? And then pounds to newtons. We hardly ever do that, but it's there, okay? Now, what they do in the grocery store, if you've ever seen the scale there when you're weighing your bananas or whatever, what are the scales they have on the scale? The scales, numbered scales they have on the scales doing the weight. Pounds on top and second, kilograms. Those are not weights, those are masses, okay? So that's really not a fair comparison. You're comparing mass to weight. But since you're on the surface of the Earth, it only differs by a constant, which is related to 9.8 meters per second squared. But then you got to get other things in there too. So really they're comparing things that are very, very different. They should be pounds to newtons, but no one knows what newtons are anything except physics. Okay. And the other side of that coin is, in the U.S. customary system, what's the unit for mass? Anyone know? No one ever uses that. It doesn't even have a part of a abbreviation for it. You have to spell out the entire word, but no one uses it. Sort of gross sounding. Have you ever gone to the store and asked for so many slugs of tomatoes? Yeah, it's a slug. That's it. No one uses it, so we strictly use weight measurements when we're talking about how much of an object there is in the U.S. customary. That's why metric is so much more precise. Okay. Now, what if we have a variable force, not a constant force? Constant forces are just way too easy, aren't they? So let's do a variable force. When a variable force is applied to an object, calculus is needed to determine the work done. Because if it's a variable force, that means it's described by some kind of curve. You can't just do force times displacement because it's varying every bit you displace. Because the amount of force changes as the object changes its position. For instance, force required to compress a spring or stretch a spring, either one, it increases. If you've ever played with a spring before, you can pull it a little bit, and you can probably stretch most springs a little bit. Okay, not the spring in your car probably, but most springs you can. But to stretch it more, you have to supply more and more force to give the same change of displacement, because it's pulling back at you with a variable force. Or when you're compressing or stretching, either one. Okay? Compressing or stretching. That goes by good old Hooke's law. And we'll probably hit that in a little bit, but not yet. Consider an object that is moved in a straight line from x equal A to x equal B by continuously varying force. And since it's varying, you do it f of x. If it's constant, f is fine. If it's a varying force, it varies with the displacement. Let delta be a partition that divides the interval A to B into n subintervals. This sounds familiar, doesn't it? Where A is your first boundary, x of 0, and then you have x of 1, x of 2, and you go all the way up to x of n, the last one being your B. That's your interval A to B. Let your delta x of I be x of I minus x of I minus 1, x of 7 minus x of 6. You know, that would be your delta 6, okay, delta x of 6. For each I, choose a CI. Think of that as center. It doesn't have to be center, but it's just some value in between x of 6 and x of 7, or x of 5 and 6, whatever. This is some value in between, okay? Now, then at that C sub I, the force is F of C sub I, okay? Because F is continuous, not jerking and being different from place to place. You can approximate the work done by moving the object through the I subinterval by the increment delta W sub I. That's the work done in that little bitty subinterval from x sub I to x sub I, x sub I minus 1 to x sub I, times your alpha C sub I, which is somewhere in the middle of that, times your delta x sub I. This is almost the work formula again. Okay? Even though it's a variable force, if they're small enough increments, this is approximated really nicely. Okay? So if that's your delta x, you force here and the force there, over a delta x there, you can estimate, that that's constant, approximately constant, right in between, as long as that's a small enough delta x. Okay? Now, so the total work done is then the summation. They didn't like this, so they blocked it out, I guess. And I don't know if that was intentional. Maybe they messed it up. And it's the summation of from I to N, that covers the whole range there. Alpha C sub I, that's your force in the center or somewhere, times your delta x. These are close to being constant, okay, if the increment is small enough. And then if you continue making the increment smaller, making the N larger, you can take the limit as that partition goes to 0, that makes the N go into infinity, and that would be the integral of alpha x dx. We knew that was coming, didn't we? Okay. A to B are the boundaries of that. Does that make sense? Real simple formula. Force times displacement, that's going to be work. Summing all these little ones together to get incrementally smaller to get the total work. Okay, so here's a definition as if we hadn't just said it. If an object is moved along a straight line by a continuously varying force, F sub x, then the work done by the force as the object is moved from x equal A to x equal B is given by W is equal to the limit is the del, your partition goes to 0, maximum length of that partition goes to 0, as the I going from 1 to N, where N is going to infinity, is going to 0, of the delta Wi, that makes sense. Then this delta Wi, that's the integral from force times displacement. Like you just said, but they had to write it as a definition. All right. The following three laws of physics were developed by Robert Hooke, Isaac Newton, and Charles Coulomb. Okay, Hooke did Hooke's law. Newton did Newton's second law. We'll get to that. Coulomb does, of course, Coulomb's law, which is electric forces. Okay, Hooke's law. The force F required to compress or stretch a spring within its elastic limits. Y'all know what that means? Elastic limits mean that when you release it from whether you stretched it or compressed it, it returns to the original. That's what elasticity means. It doesn't mean that it stretches. It means it returns to its original shape. Now, if you can imagine a slinky, do any of you remember slinkies? Those are basically springs, very, very weak springs. But you could take that thing and stretch it until it was almost straight and then it never go back. Before that, it always goes back to the original shape. So you pass the elastic limit if you spring the spring, okay? You sprung the spring, okay? So within the elastic limit, then the Hooke's law says the force necessary to compress or stretch a spring within the elastic limit is proportional to the distance that the spring is compressed or stretched from its original length. That is, F is equal, okay. Proportionality means F proportional to displacement. To change the proportionality to equality, F is equal, the proportionality symbol goes to equal K, always. That K is called the constant proportionality, often called Hooke's law, Hooke's proportionality law. Okay? It varies for different springs. The slinky, it would be an incredibly small number. For that coil spring in your car, an enormously large number, okay? So opinion of that. Now, where K depends on the specific nature of the spring. What materials it's made of, how tightly it's bound, all that kind of stuff. Now, what you have to keep in mind, and it really doesn't matter, it's only difference by a sign. The force required to compress or stretch a spring a distance d. The spring a distance d. So if you're compressing a spring a distance d, then the force is in the direction of the compression. Okay? If you're stretching it, then it's this one. Now, a lot of times this is written in the sense of what's the reactive force, which then is an opposite sign. This is giving it with the same sign, so it does make sense and it's a lot easier to use. Okay. Newton's law, this is gravitational law, or it's going to be, this is Newton's law of universal gravitation. The force F of the attraction between any two particles of any two masses, M1 and M2, proportional to the product of the masses, inversely proportional to the square of the distance between them. So the product of the masses, direct proportionality, inverse meaning 1 over the square, inverse square law, and combine all the proportionality constants of that G. And that G, universal gravitational constant, in SI units is 6.67 times 10 to the minus 11 cubic meters. No. Oh, okay, got it. Okay. Usually you say square, but because it's a square down here, but the units are right. They're just weird. Cubic meter per kilogram second squared. That's a strange unit where G is the universal gravitational constant. That number there. Most of the time, I would say that would be in newtons times squared centimeter per kilogram squared. But they left the Newton out and put in the other. So don't worry about the units. They work out. Okay? That's just a weird one. Coulomb's law is the force between two charges. Q1, and by the way, this is a variable force because as the distance between the forces vary. The masses aren't going to change. I mean, masses usually are fairly constant. It's the distance between them are changing. So that's why that's a variable force. Okay? And then Coulomb's law, and that's the inverse square law, and so is Coulomb's law. I mentioned this before. The force between two charges, Q1 and Q2, in a vacuum, proportional to the product of the charges, inversely proportional to the square of the distance between them. Looks very similar, doesn't it? This was the G before, M1, M2, B squared. So they're very, very similar, except, of course, masses up here are very different from charges. Q2 and Q1 and Q2 are given electrostatic units. Okay. And D is in, oh boy. So that force would be in dynes for a value of K1. Okay, interesting. They chose electrostatic units, which are nowadays called U. That basically is the charge on an electron, I believe, is what they mean by that. So I've never seen it written quite this way because I don't usually use it in dynes or cents. But anyway, that's Coulomb's law. Very, very same form, similar form to gravitational law, inverse square law. Okay. So let's do example 2. Y'all been waiting patiently for example 2. Okay, let's get it done. And by the way, in your text, there's a picture of Emily de Bretuil or something like that. A major work of hers was the translation of Newton's Principia, which was written in Latin, into French. Her translation and commentary greatly contributed to the acceptance of Newton's science throughout the rest of continental Europe. In general, Britain back in those days considered the English Channel a pretty major dividing line. So the continent in England, they didn't do a lot of things. She helped overcome that with Newton's laws. Didn't work so well with the argument over who invented calculus. Continental Europe tended to go with Leibniz, whereas the Britain stayed with Newton. And but here she did. Now, you would think just a translator, why would she be mentioned? Notice here it said, and her commentary. So she was a very bright woman. She didn't just translate things she didn't understand. She commented on them and gave them a lot more oomph, you might say, to the French or the European audience. Okay, so let's do example 2. And by the way, this one is also, you can see larsoncalculus.com for an interactive version of this type of an example. So here we have a force of 30 newtons compresses a spring 0.3 meters from its natural length of 1.5 meters. Find the work done in compressing the spring an additional 0.3 meters. Okay. Now, you might have a urge to just do a proportion here and see if you can get that to work. Don't, because this isn't constant. This is a variable force, okay? So just to sit down and do a proportional here, that doesn't work, okay? You have to do it step at a time. So you take the first bit of information that we have, and when you're dealing with springs, what do we use? Hooke's law. How does that go? Alpha is equal to kx, right? Or kd, they say in the book. Okay, I'm used to saying kx. Okay, kd. Hooke's law in the text. Okay, now this d is the amount of compression from the original length. So this 1.5 meters really isn't going to matter much here, because what you do, the force given is 30 newtons, and let's leave it in newtons, is equal to k times the displacement is 0.3 meters. So the first thing to do is calculate k. So we'll divide both sides by 0.3 meters. Now, I was starting to say let's convert newtons to its fundamental units. No. Usually we refer to k in units of Newton per meter. So this would be what? Yeah, okay. Yeah, if you move the decimal one place and then divide by 3. So k is equal to 100 Newton per meter. Okay? Now find the work done by compressing the spring an additional 0.3 meters. Okay? Now, let's go back and plug this in. And this, by the way, remember, is a variable force, so that's why I like to put x in here. And this would be 100, and after a while I will leave off the units, but for right now I'm going to put them in. 100 Newton per meter times your x, okay? Because that is the formula, okay? This part just tells you what k was. Now, if you go back to here, this is what we use to get the work done, okay? So let's go back to the work done is the integral, of, and where are we going from? You're starting at 0.3 meter and compressing it an additional 0.3 meter, so you're going from 0.3 to 0.6. That's how you do this problem, okay? And then your force is going to be 100x, I'm going to leave off the units now, times your dx, okay? Which means, of course, you can pull the 100 out front and do the integral from 0.3 to 0.6 times of x dx. What's the antiderivative of x dx? X squared over 2, evaluated from 0.3 to 0.6. Okay? Now you can take the 2 here, divide it into that, and just do a 50 out front. So let's just do a 50 times 0.6 squared would be, second, 0.36, is that what I heard? Okay, good. Okay, minus, next one, 0.09. Okay, I was starting to do 0.9, said that doesn't work. No, there's a 0 in there. So the difference between those two is 0.27, is that right? So 50 times 0.27. With a calculator, you can probably do it pretty quick. 13.5. What unit? Joules. Excellent. Now, whether they keep that many digits or not, yeah, this is a math book, so yeah, they probably will keep them. If this were truly physics, when you look at everything given there, this is either 1 or 2 significant digits. You can't tell because you don't know about that 0. That's only 1. This is 2. That's only 1. You can only do 1. So you would approximate this to be about 10. Okay? Now that's not very precise. Okay? But you really can't do any better because you only have 1 significant digit. This being a math book, they don't care about significant digits, so they left at 13.5, which at least sounds like it's a much better measurement. Does everybody see how they got that? All right. All right. Well, let's see. Let's watch them do it then. That was my rendition. Let's see how they do it. By Hooke's law, the force required to compress a spring x units is F of x equal kx. That's what we had. Because we knew that the first 0.3 meters required a force of 30 newtons. So the next 3 wasn't going to be 30 newtons, by the way, but never we'll do that. It follows that F of 3, and you just do that Hooke's law, you get K equal to 100. That's newtons per meters. I like to think of that. So F of x equal 100x. It's shown in this picture. That picture shows us 100x, doesn't it? I guess with the numbers in there. Okay. Now, what you're doing down here is pressing another 0.3 meters, so they don't show you that. But that's the setup for the rest of the problem. Okay, to find the increment of work, assume that the force required to compress a spring over a small increment delta x is nearly constant. So then the increment of work delta w, increment of work, is the force times the distance increment, which would be 100x, that was your force, times delta x. And because the spring is compressed from 0.3 to 0.6, I'll say an additional 0.3 meters, the work required is the integral from a to b of f of x dx, which is 0.3 to 0.6, of 100x dx, which is 50x squared, evaluated from 0.3 to 0.6. And they use all the numbers in there. Great, good for them. 18 minus 4.5 is 13.5 joules. Okay, got it? So they didn't quite do it the same way we did, but we use the same principles. Okay. Note that you do not integrate from 0 to 0.6 because you're asked to determine work done by compressing the spring an additional 0.3 meters, not including the first 0.3 meters. Okay. All right. The summation of increments in the form, this is your delta W, increments of work, is force times the increments of distance, displacement, F times delta X. Another way, though, to do it is to do the increment of work is the force increment times the distance. So you're doing different forces over different increments there, but the same distance along the way, so that would be a delta F times X. That second interpretation of delta W is useful in problems involving the movement of non-rigid substances such as fluids, chains, ropes, those kinds of things. Then the amount of force is the variable and the distance is fairly constant. Okay. A spherical tank of radius 8 feet is half full of spherical tank, the peach outside Clinton, okay. Spherical tank of 8 feet is half full of oil. No, that's not that peach, okay. That weighs 50 pounds per cubic feet. The oil weighs 50 pounds per cubic feet. And find the work required to pump all of the oil out through a hole at the top of the tank. Okay. This has promised to be a very fun problem, doesn't it? So let's do our best to draw a picture. Okay, let's imagine that's a spherical tank. Okay, some type of a spherical tank there. All right. It is half full of oil, so the oil is down in the bottom half here. Okay, the oil has a weight of 50 pounds per cubic foot. That's really a weight density. Let's do D sub W, weight density. That's not always a symbol for it, but it is sometimes. Find the work required to pump all of the oil out through a hole at the top of the tank. Here's your hole, and you're having to come down here and pull the oil out and pump it out of the top of the tank. Okay? So what we do here is do little increments of oil, a wedge of oil here, okay? A layer of oil, okay? And in this case, your thickness of this is the constant, and the weight of this, which is your force, is the thing that's, how do I say that? Sort of everything's varying. Your distance you're pumping it is varying, okay? And the amount that you're pumping from that distance is varying. So there's a lot of variation going on in there, okay? So you first basically need to determine the volume in this disk of oil, you might say. Okay? Now, in order to do that, we know here the radius is 8 feet, which is also this radius up here. Same radius throughout a spherical tank. Okay? But this layer down here is being pumped a distance. Okay? So let's set up our coordinate system. Doesn't really matter too much, but let's have the center of the tank at the origin. And then the distance that you're pumping that, let's see, I don't think they do it. I think they put it at the bottom, don't they? Yeah. Okay. And there is a reason for that, but so let's put the center down here at the bottom of the tank down there. Okay. Now, the height that you're pumping the oil, okay, let's take this representative thing. Okay, this is your y, of course. Since you put the axis down here, here's y. Okay, the thickness of this, of course, is your dy. So, the distance that you're pumping that would be 16, because this is a radius, so twice that, the diameter would be 16 minus y. That is the distance that you're pumping. By that? Okay? That layer right there that we're talking about. Okay? Now, while we're there, let's get the radius here of this layer, because we're going to need that to calculate how much you're pumping. So this, let's call this a little r here. I'm real tempted to just call that x, okay? And certainly is x, and truly it is, so let's just call that x then, because you put the y-axis right through the center of that, so that radius is just actually your x. Okay, we're going to have to come back and do some maneuvering here, but that's okay for now. Okay, now how is that x related to, and this is part of the problems here, how this x is related to that y. Okay, and it doesn't seem to be a huge connection there. Okay. Well, it's more closely related to this distance. And this distance is 8 minus y, because it's 8 from the south pole to the center, that's the radius there, minus y, that would be that one. Now, looking at this then, and you know this is 8 here, because that is actually a radius there, so you can say that x squared plus 8 minus y squared is equal to 64. 8 squared, right? So you want to get your x in terms of y's, so x squared is equal to, okay, let's do this, expand this binomial here. 8 squared is 64, right? Minus 16y plus y squared. Is that a proper expansion? Okay, let's subtract it from both sides. The 64s are going to go out, and that gives you 16y minus y squared. That's what x squared is, and I think we can leave it like that. And there's a reason for that in just a minute. Okay? So let's right now leave it just like that. Okay. So that gives the radius of that slice of oil. Does that make sense? Okay. The volume of that slice of oil would be the area of that slice of oil times the thickness. Well, the area of this slice of oil, let's call it delta A, maybe. Well, let's just call it A. A is equal to pi times the radius, which is x squared. Hey, that makes it pi times 16y minus y squared. That's why we didn't have to go back and change that. Okay, then take that and multiply it by the thickness, dy, and this gives us our dv, change of the little incremental volume. Now that little incremental volume we multiply by 50 pounds because the 8 was in feet, so you got cubic feet there. So your delta weight, not to confuse that with W. Let's call it delta force sub W. That's weight. Weight is a force, so that's delta F, the weight increment. And that would be 50 pi times 16y minus y squared dy. That's your incremental force. Okay? Now, your displacement, how far do you displace it? That was your, there it is, 16 minus y. Okay? So that's how far you had to lift it. So that's your weight that you had to lift, because this is pounds per cubic feet times cubic feet. So that's your incremental weight, and then the distance you lift it is that. Whew. So the work done, this is capital work, that's weight now, I mean work, not weight, is, and let's bring out the constants here, 50 pi times the integral. Now this integral is going from I don't guess it really matters where you do the bottom slice first or the top slice first. It really doesn't matter. So let's do it as y is going from 0 to 8. Let's try that. 0 to 8. This will be in feet. And then your work the 55. Now, it's force times displacement. And you'll notice this can be factored as y times 16 minus y, right? So basically what we have is a y times 16 minus y squared dy. I sure hope I've got that right. This is really a pain in the neck to have to do. Not that it matters, okay? Because you got to multiply them anyway, so it doesn't matter how you multiply them. To me, this will make it a little easier, maybe, to multiply, because it will be y times 16 squared. Anyone know that one? 256, is that right? Okay. Minus 32y, right? Keeps disappearing on me. Plus y squared. Okay. That's that thing squared. Then multiply it by y, and you get, this will be a y, that will be a y squared, and this will be a y cubed. Okay. So that's what's going to be in the integral. Finding room to do it. So the work is going to be 50 pi times the integral from 0 to 8, that thing, 256y minus 32y squared plus y cubed dy. I think I've got it all right there. Yeah, that's what they have to. So, what's the integration of that? W is equal to 50 pi, which is a big number in itself, antiderivative of 256 y. Anybody? Perfect. Minus nothing you can divide out there. 32 over 3y cubed, right? Next, over 4. We evaluate that from 0 to 8. I'll let someone with a calculator do that one, okay? 50 pi, I'll leave that alone for now. 64 times 128. That's the small number. Right? Y'all can plug that in, I hope, right? They get, of course, 11,264 divided by 3 times 50 pi, which comes down to total answer being 589,782 foot-pounds. Approximately, okay? Now, no way you can get 6 significant digits out of that, okay? I think you would be safe to say approximately 600,000 foot-pounds. Oh, y'all let me get away with that. I put foot per pound. That's not. That's foot-pounds. That's a dash there, not a slash. Okay. About 600,000 foot-pounds. Okay. Because you just don't have the significant digits to give that many digits as an answer. Now, here's what they suggest. Let's just estimate the volume of this. That's 1/2 of 4/3 pi r cubed, right? The volume of the sphere is 4/3 pi r cubed, right? And half of that would be 2/3 pi r cubed, right? So let's just do that. 2/3 times pi times 8 cubed. So we'll do that here. 2/3 times pi times 8 cubed. Say again?
512. That's all.
Okay. And then multiply that by, why not 10? Okay? It's 8, but you know, some of it's lifted more, so let's just say 10. So that makes pretty close to this. No, what did you say your answer was?
I got 512, but this is a weird calculator. I might have done something wrong with it.
Okay. But anyway, the book says, I thought I was on the right page. You know, we skipped example 3, didn't we? I didn't realize they skipped example 3 until just now. I looked back and said, wait, where did that come from? They said about half of that is, you said 53,616 or something like that? Or you didn't say that? I thought I heard 50 something. That many pounds, and then do it. They said 8, I said 10. That would have been 536,165. 589,000. Hey, close enough. They're both about 600,000. Okay, so yeah, you got to figure you're in the right ballpark. All right, let's see how they did it. And then if we have time, which I don't think we, we're already past time, aren't we? Okay, now what, sorry about this, I didn't realize till now, I just happened to glance, we didn't do example 3. So you're going to have to remind me next time that we're going to start with example 3, and I think I'll remember, but who knows, when we start to do example 4 that we've already done it, okay? So we've already done 4, and we'll move on to 5 and 6 the next time. 7.5, you can do any odd, either 5 or 7, they're both at Calc Chat. 7's at Calc View. Any of the odds, 9 through, goodness gracious, 9 through 13, they're all at Calc Chat. 11's at Calc View. And I think we'll have to stop and wait till we finish some of the others before we do the others. The pumping water you could do, that would be number 21, or 23, or 25, or 27. So you can do any of those, 21 through 27, any of the odds, they're all at Calc Chat. We'll have to do the propulsion one in between, so I'll get that in a minute. Good deal. Any questions? All right. Just to look ahead a little bit here, we're almost through with 7.5. We've still got 7.6 to go. I can't remember if I do. Yeah, we do that. And then 7.7, I believe we do also. Yes, we do that also. And so, got a little bit of time. May get to it at the end of next week or the first of the following week for that first test. Long chapter to begin with. With 6, whatever that was. No, I'm sorry. This just started in chapter 7. Okay. We'll get it done. Good deal. Have a good weekend. Working on calculus will make it good, won't it? Good deal. Okay.